Good afternoon, guys. So, my name is Alex Westerland, and I'm about to give you guys a presentation that will blow your mind and is something you will probably remember for the rest of your lives. You guys ready? Woo! All right. So I'd like to introduce you guys to something called Project Endor. And this is a project I've been working on for about a year and a half now, and it's very personal to me because it is a very big, ambitious thing, and it's something that I really think will make a difference for a lot of people in this world. Let's begin with a question. What is the biggest threat to our civilization? Anybody know? Sea level rise. So, sea level rise is a big deal. Here is a chart from 4 NASA satellites and like 10,000 data points that I made, showing the average sea level from right around the time I was born. As you can see, it's going up. The ocean has been going up for a long time. This is just when we started having satellite measurements, so they have a very high degree of accuracy. But it has been going up for a very long time, and in fact, that rate is accelerating. There's a problem with this. And that problem is that 1% of humanity lives within 1 meter of sea level. That's a lot of people. Those are our cities and our towns and our ports. That's where all of human infrastructure is. Our global connection to trade, to resources, to languages and religions, all of that is near the ocean. It's on the coast. And so a small rise in sea level will disproportionately affect the human species more than any other species on this planet. So the question is, of course, what can we do with the extra water? We've got more water in the ocean now, and it's adding, and it's adding, and it's adding. The ocean is going up. Where can we put it? If you have a mess in your room, of course, you shove everything under your bed. Where are we going to put the extra seawater? How many of you guys have gone to the beach? And you guys have gone just close enough to the shore, and then you dig this hole in the sand, and just high enough for the waves to wash up to it, but not wash it away. And then when the wave washes out, it's full of water, right? Technically, you have just lowered sea level. You have just lowered the level of the entire ocean around the world. And you've done that by digging a hole. Now, the ocean is a much bigger problem than what a couple kids on a beach can handle. So we need a bigger hole. Let's dig a hole. Nah, I'm just kidding. That's a really big hole. We're not going to dig one. But maybe we can find one. Here we have a map of the world. It's beautiful. And in doing my research, I found a few around here. Up there, down there. We have in the middle, and we have off to the side. That is the American Great Lakes, the Caspian Sea, Lake Baikal in Russia, and the African Great Lakes. All of these are very, very large holes that hold a lot of water. Well, they're already full, though. I can't put seawater in there because they're already... Darn it. Okay, maybe we have an empty one. So I did some more research, and these are the biggest depressions of land, the lowest points on Earth. But now, a hole needs to be not just deep, but wide, like a bathtub, not a narrow cylinder. Let's look at the surface area of these depressions. Put those two things together, you have both a wide and a deep area that we can then fill with water. Let's look at these three. These are the three biggest ones by surface area, right? 48,000, 20,000, and 10,000 square kilometers. Each of these, by the way, are about as big as an American Great Lake, for reference. So these are very large. These are the three depressions we were looking at. You've got the Qattara Depression, the Danakil Depression, and then the Turpan Depression. Now, can anyone tell me what two of these have access to that the other one doesn't? Well, if you look, these two are right near the ocean. That one is very, very far, right? If I'm going to pick up seawater and move it and then put it in a hole, I would much prefer that hole to be as close to the shore as possible, right? The Turpan Depression is way too far away to even justify even thinking about that. As you can tell, it is 2,500 kilometers to the nearest shore. And that is if you tunnel directly through the Himalayan mountain range. So we're going to cancel that one, and we're going to look at the remaining two, the Qattara Depression and the Danakil Depression. The Danakil Depression looks like this. It's kind of an eerie landscape. right? So what you see here are big toxic pools of crazy environments, boiling water, acidic solutions, all of this stuff, right? In fact, NASA astrobiologists come here because it's very difficult for life to survive here, but there is still life in all of these crazy pools of water, right? That's pretty cool. It's also got some nice mountain ranges and all that stuff, and a few active volcanoes. And in fact, in these mountains, the earliest human fossils in history have been found, millions of years old. It's phenomenal. This area, the Danakil Depression, is considered the cradle of humankind. So let's not fill it up with water. All right, let's see what else we have. This is the Qattara Depression. It is full of sand. There's really not much else there. It's a big, open, sandy place. A very long time ago, it was a lake, just like the American Great Lakes, just like the Caspian Sea, just like those other places I showed you. This was also a lake. The difference is it is dried out. So we have here a prime candidate. It's close to the shore. It's massive, and it might be able to make a difference and actually help us fight sea level. So we're going to fill the Qattara because it's way easier. So let me introduce you to the Qattara Depression. The Qattara Depression is located in Egypt, just a little bit away from Cairo. You can see this darker patch right there. That is the edge of a series of cliffs. Think of the Grand Canyon, but a little bit smaller. To put in perspective, using satellite imagery, this is what it will look like. That is larger than the Nile River Delta. Astronauts love to photograph the Nile River Delta from space. We have astronauts orbiting the International Space Station full-time. We've had them up there for decades. And they love to take pictures of that because it is the most easy to recognize thing when you are flying miles and miles above the Earth. You can see that. So imagine what would happen if something that big showed up right next to it. Now, let's zoom in a little bit more. So here we have the proposed Western Sea. It's about 60 kilometers from the coast, and there's a couple different ways we could connect it. We could dig a canal. That's sort of the classic way of moving water around the world. The Suez Canal, for example, is nearby, and that is a very, very widely used canal, and it was built a very long time ago. No modern technology was involved. Our other option is we could drill a tunnel, like a subway tunnel or a metro tunnel, right? We could drill a tunnel and go right through the landmass, connecting the shore to the depression of land. Now, why is drilling a tunnel cheaper? Good question. So there's this plateau in the way. The land is not kind of like close to sea level. It kind of shoots up, and it's, well, let's just say it's easier to dig out that much dirt compared to that much dirt. So this is the proposal. A series of 4 large pipelines spread out across the coast and with 2 primary inflows into the depression. Now, why is that? That allows redundancy. You'll have these large inflows. Looks kind of just like a standard sewer drain on the coast, but water's flowing in instead of out. And these are large enough for you to go through with a small boat. The redundancy is very important here. These are very long tunnels. You're sending a lot of water through them. You need to be able to shut down 1 or 2 here and there to repair things. In the depression, you have 2 outflows. Those 2 outflows, one of those is enough to maintain the lake's level. 2 of them allows you to raise the lake's level. So we need to get both of them operational, and that will allow us to fill up the lake. And then, because it isn't in the desert, water will continually be evaporating. We will have a continuous inflow that could be justified and handled with 1 of those. And that will allow us to shut down either side to ensure that at any given time we can maintain the level of this artificial lake. Now let's talk about the impact. Because this is huge, this is crazy, this is ambitious, this is something you've never dreamed of happening. So, obviously the first one is direct water storage. It is a big hole in the ground, as we've been talking about, and if you fill up that big hole in the ground, you're going to hold a lot of water. How much water? Well, 1,000 cubic kilometers. That's equivalent to 3 millimeters of sea level. The entire world, we will actually lower the sea level by about 3 millimeters. We're going to fit all of that into a little lake in the Egyptian desert. That's an entire year we can erase from the record. Over time, that's going to give you about a 6% decrease in sea level rise over decades. We're going to basically slow down sea level rise around the world. And all of that's going to be possible through this. Now, I just threw some numbers in your face, and that's fine. What is 80 cubic kilometers per year? That is the volume of Niagara Falls. Niagara Falls has roughly that same amount of water flow over it every year. So this already exists in nature. We're just creating another version of that, another iteration of that. Next, heat sequestration. This is a big word, but basically it just means we're going to take the heat of the Earth and we're actually going to store it underground. How many of you guys have had tap water? Obviously, right? How many of you guys have been in a cave or something like that? It's cold, right? It's cooler than the outside air, no matter, even if it's really hot outside. That's because the ground is a constant temperature, year-round. Rain, shine, sunlight, snow. The ground is the same temperature once you go down just a little bit. All of this, remember I said we're drilling a tunnel? The water that flows in there is going to be altered. So let me give you an explanation of that. Here we have a simple diagram, Mediterranean Sea, Qattara Depression. A lot of people think the oceans are warming up and that it will look like this. It turned red, right? In reality, it looks like that. It's just the surface of the ocean that's warming. Just like the ground, once you go down a little bit, basically below your toes when you're swimming, the temperature of the water is the same as it's always been. Remember that tunnel I said we'd drill? Guess what water is flowing through that tunnel? Now, I asked you guys earlier, has anyone ever drank tap water? You guys all raised your hands, of course. The ground will cool off that water as it flows through. We're actually going to take the hottest water in the Mediterranean Sea and channel it and store all of that heat in the ground here beneath this plateau. And then out is going to flow nice, cold water. That is going to change the equation where before we have global warming, we've got hot surface level ocean water, and turn it into air conditioning. That's because all of that cold water, once it's cooled off, is exposed. And so it's going to start absorbing some of the desert heat in the Sahara Desert and cooling off the local environment. So we're actually going to be cooling the planet just by drilling a little tunnel and sending some water through it. And on top of that, the carbon dioxide that you can store in water actually goes up. As you lower the temperature, the amount of carbon that you can dissolve in water goes up. So the colder water in this lake that used to be over here is going to get colder and then suck carbon dioxide out of the atmosphere like a sponge. It's going to absorb 500,000 tons. That's pretty cool. Now, number 3. We are actually going to bring rain to new parts of the world that haven't seen it in a very long time. So here we have the wind patterns for most of the year in Africa. As you can see, most of the wind here is blowing south. And then it hits the lower part of the Sahara Desert, and then it shoots across into the Atlantic. All of that, when you put a lake right there, is going to bring rain in that direction, somewhere in that area. I don't know where. That requires advanced climate modeling to work out. But somewhere in that area, because we've increased the amount of water for which moisture can evaporate from and flow through the air, we can actually increase the amount of rainfall somewhere downwind in this area. Now, the wind is not the same all year. So about 3 months of the year, the wind direction changes, and it blows in this direction. This is the Sinai Peninsula. The wind is going to blow that moisture in that direction right into the Sinai Peninsula. Now, if we zoom in a little bit, the Sinai Peninsula is a big mountain range right here. If you guys have ever been near a mountain range, when moisture flies through, it hits the mountains, flies up into the atmosphere because there's a mountain in the way, and it cools off. And as soon as it goes across the mountains, down it comes as rain. This is the most reliable prediction we can make in terms of climate impact in this area. And if you look in this area, I've got a satellite scan from the European Space Agency. Look closely at this area. It's tan, it's brown, right? It's dry. But if you enhance the image with a little bit of satellite data, you can get that. There are actually ancient riverbeds in this entire peninsula. This area used to get regular rainfall. 6,000 years ago, this area was green, like the savanna. It's full of life. It already had rain before. We're actually restoring a lost ecosystem. And finally, cool thing number 4, seawater mining. Now, odds are you guys have never heard of this, and that's okay. Seawater mining is the big economic benefit from this system. If you're trying to get a resource, say iron, you can find a lot more of it in any certain amount of land compared to any certain amount of ocean, right? You're not going to find blocks of iron floating in the water, but the ocean has every element on Earth dissolved into that water. It's just spread out. You need a lot more water to get the same amount of resources. However, if you do the math, there is a lot of water on this planet. Now, people have tried seawater mining for a long time. This is the latest technology, and basically what it is it's just like a seaweed, basically a big ball of yarn stretched out, and they deploy it along the seafloor. And it just drifts in the sea, just like seaweed. But it's an absorbent fiber, and what those fibers do is they absorb all these little particles of iron and gold and platinum and copper and whatever else is floating in the water. And these systems are actually borderline cost competitive for certain elements already, even though it takes boats and ropes and all of this stuff to get it to work. And they're passive, right? It's just catching whatever's drifting by in the water. Let me give you an example. Where is the most dust in this room? If you look on top of a bookshelf, maybe you'll find some dust, right? That is like finding a resource on land. However, there's more dust in the air all around us than you'll find on top of that bookshelf. That is what's in the water. Now, how do we get that dust out of the air? What do most buildings have? They have a furnace, an air filter. You take all of the air and you run it through a system, through a filter, and then you send it back out. Right? If only we had a giant thing we could run a bunch of seawater through. Oh, look, it's a big pipe. We can run all the ocean water through that, and it's a controlled system. This is our filtration system for the world's oceans. We can pull out tons and tons of resources from the ocean in extremely large volumes. Remember, I showed you, it's Niagara Falls. That's the amount of water flowing through these pipes. That is enough water to harvest a large amount of resources, enough to sustain entire economies. And we can do all of that with this. Those systems are already cost competitive when you drop them off like boats in the coastal waters. All you have to do for this, look closely here. All you have to do is put that at the end of the pipes, a filter. It's much cheaper, much lower operating cost, and you will have a much, much, much higher yield because all of that is actively flowing through. It's not catching things that are drifting in the currents. Let me go through a little bit of data real quick. This is just one example of some of the things that some of these seaweed-type materials have been able to harvest. Magnesium, vanadium, uranium, sodium, iron, zinc, copper, whole bunch of things. We can harvest them in large amounts. And depending on how we change the materials of that, we can optimize them for whatever resource is in most demand or can make the most money based on the world's demands, right? To give you one example, just one, that's uranium. We can harvest a little bit. More than you'd expect, actually. However, uranium is a limited resource. It's going to run out in the next 200 years, just like fossil fuel. The amount of uranium in the world's oceans is enough to power all of the human species for the next 1,000,000 years. Seawater mining is a revolution in eco-friendly resource acquisition because there's no destroyed environments. We don't have to chop up a rainforest to mine for this metal in this part of the world. We don't have to use toxic acids to draw veins of resources out of the rock. It's just a filter. That's all. Now, I am a logic-brained person. I love that. Charts and data and all the stuff I just showed you, that is the stuff that I love. But there were a lot of numbers, there were a lot of charts, and not everybody understands that stuff or cares about that stuff. A lot of people like a different form of presentation. So I'm going to tell you guys a story. So we're going to start up here. If you guys remember the chart I showed you earlier, that is where the outflows are. So it's day one. The first tunnel has just opened. We're doing early water tests, sending little bits of ocean water down it to make sure it flows from one end to the other end. If you're sitting on that cliff, you see a small stream come out. just a little bit. It'll probably evaporate after, a little bit floating into the desert. It's pretty hot. But that's the ocean water. That ocean water is going to travel right along here to the lowest point in the depression, right here. That's the deepest part of this area, where eventually it will pool together into a lake. It won't take long, because this is the desert and it's very hot, that it will start to evaporate. And when it evaporates, we will get rain. The first rain some of the Sahara Desert has seen in thousands of years. It's going to create something called a desert bloom. Most of you guys probably haven't heard of this. Sometimes they're called super blooms. If you look into almost any desert in the world, when they get rain after even 100 years, they'll have flowers come up, and bugs and critters, things that you never knew were in the sand. In the most barren wastelands on Earth, they're actually full of life. They've just learned how to hibernate through hundreds of years of dryness. It's not going to be that hard to change the face of the Sahara Desert. It's just add water. As more and more water begins to flow into this area, it's going to start to fill up. Some of this area, in what used to be random desert formations and rocks, is going to turn into rocky outcroppings along the coast. This, and I want to stress this to you, is bigger than you can imagine. This goes on to the horizon. When you are standing on the shores of this lake, it will feel like you're standing on the shore of the ocean. This water, remember how I told you it's going to go through a filter? This water is going to be the cleanest, clearest water you have ever seen. Moving over. The eastern shores of the depression have a lot more sand in the area, so your shoreline's going to look like this. It's going to be a beautiful desert beach. Moving up here, this entire northern face is a cliff, extending 100, 200 meters high at the highest points. Where that cliff meets the sandy shores down here, you're going to get beaches. This is where everyone's going to flock to see the West Sea. Looking at these cliffs, they're going to look like this. They're going to be absolutely beautiful. So, in conclusion, let me wrap up all of this stuff that I just threw at you. We are going to build the 6th largest lake in the world. It's going to store water. It's going to store heat. And it's going to store carbon. It's going to restore a 6,000-year-old ecosystem. It's going to be a breakthrough in environmentally friendly resource acquisition. And on top of all of that, it's going to be beautiful. Thank you.